Okay, so Chapter 4, Section 9 is about oxidation reduction reactions, which are oftentimes called redox reactions. All right, and oxidation reduction reactions are dependent on oxidation state or number. And combustion, I say "and" with a question mark here, is because combustion reactions really are redox reactions. Okay, we've done combustion reactions before, but we're about to look at them in the context of redox. Okay, before I begin, let me define oxidation. So oxidation is loss of electrons. Reduction is gain of electrons. Okay? So oxidation is loss of electrons. Reduction is gain of electrons. All right? So oil rig, as you can see, is a mnemonic that I have used for years to remember which is which. Let me say it differently. That if you have some compound and you gain electrons, or not compound, if you have some atom, some species, some atom, and it gains electrons, it's going to go to X minus, right? Well, that is the gain of electrons. So this has been reduced. Reduction. Okay? If you have some species and it loses an electron, right? What's left? X plus. It has been oxidized. Okay, too many dots. There was a dot in my X. So, all right. So going from here to here is a reduction, and going from here to here is an oxidation. Can you see? So it looks like if I'm going to gain electrons, my charge is actually going to go down. Okay, so that's the definition of oxidation and reduction. Oxidation state is something we're going to define here a little more carefully in the next few slides. Okay, so oxidation state here. Let me start out. I've got a list of rules that are on page, I think, 160, page 161. But before we go to those rules, I'll show them on a future slide. But for now, I just want to say a couple obvious things. Rule number 1 in that slide is that if any element is by itself, anything in its elemental state. Can you see an element here? And it's by itself. It's in its elemental state. Its oxidation state is 0. Okay, so it's kind of like charge. All right? Well, what about if you have sodium as an ion? What's its oxidation state? Well, if it's like charge, then its oxidation state is +1. Okay? So what about chlorine? What is its oxidation state? It's 0. What about chloride? It's -1. What about diatomic chlorine, molecular chlorine? It's 0, right? Because it's by itself. You see? It's got another chlorine there, but it's like its charge. And so Cl2, as you can see, it's nothing but chlorine's there. Its oxidation state is going to be 0. Okay? So the other thing, the next thing that you need to appreciate, and we're going to look at the table here in a minute, but let's look at, let's say, water. Okay? Well, you remember that if oxygen was in an ionic compound, it would have a charge of what? -2. Remember that? Okay? Well, how many oxygens are here in this compound? Only 1. So its total charge that we can thank oxygen for is -2. Well, what is its total charge? If it's just H2, it's just a water molecule, its total charge is going to be 0, right? Because it's neutral. Right? So what do I have to add to -2 in order to get 0? Well, +2, right? And I've got 2 hydrogens here, so each of those 2 hydrogens takes on one of those +1s, and sure enough, that is the oxidation state of hydrogen, and here's the oxidation state of oxygen. So what I do when I'm adding these, I think Tro does it the opposite. He puts the oxidation states below and the charges above. But what I do is I start out with notes to myself. What do I think the oxidation state of that particular compound is? And I remember that in an ionic compound, oxygen is, I think, it's almost always -2, right? So it turns out it's in group 6. Right? And can you read that from where you're sitting? -2. Remember this? Group 1. Group 2 is +2. That's too small to read, isn't it? Group 1 was always +1. Group 2 was always +2. Group 8 was always 0, right? Its charge that I wanted to have was 0. The charge that group 7 wants to have is -1. The charge that group 6 wants to have is -2, right? Here's group 7. Here's oxygen. Sulfur's below that. I think selenium is below that. I forget. So, all right. So that's why I said -2. So group, and we're going to repeat this. It's in your book, but just for now, group 6 wants to have a -2 on it. Group 1 wants to have a +1. And sure enough, they all add up, right? -2 times, there's only one oxygen in a water molecule. So -2 times 1 is -2. +1 times 2 is +2. And sure enough, the compound is neutral. We knew that because there was no charge here, right? Okay, so let's do another one. Let me go back to red. Okay, and let's say, I don't know, how about ammonia? NH3. Okay, so what did you, if hydrogen is in a compound, what is its charge typically? +1. How many are here? 3 of them, right? So that's going to give us +3. The total charge in this compound here is 0 because it doesn't say anything, right? So what must this be? This must be -3, right? And if that's -3 and nitrogen, there's only one of them, so that -3's got to be divided across all those nitrogens. There's only one. That's going to be -3, okay? So the oxidation state of nitrogen in ammonia is -3. The oxidation state of hydrogen in ammonia is +1, okay? And the reason is as I've described here below. Okay, so let's do another example. I'm going to go back and forth. I think it helps to stick with the same color. Let's go with red. And let's do another compound. I wish I could ask you what compound you wanted to do, because we could do really anything we wanted. So we've done, a couple times we've seen, let's see, ammonia or methane. We've burned it in combustion, right? You've seen me use that example a couple times in class. So let's go here and say, by the way, the question is going to be, what is the oxidation state of all that? That's how you're going to get these questions. Assign oxidation states to all the atoms, okay, or all the elements. So what is hydrogen typically in a compound? Well, it's typically +1. Okay, so there are 4 of them here, so that's going to be +4. And the overall charge of this compound is 0 because it doesn't say anything at all. It's methane, neutral. Right, and so what must this be? This must be -4. Can you see that? -4 plus 4 is 0. So we take that -4 and divide that over all those carbon atoms. Well, there's only one, so they must all go there. So the oxidation state of carbon in methane is -4. And the oxidation state of hydrogen in methane is +1. Okay, let's do one more and then we'll move on. Another compound we've seen a good bit of is carbon dioxide. Okay, carbon dioxide. Now, oxygen, remember this rule up here, right? Oxygen has a tendency to be -2 because it's in group 6. So -2, and there's 2 of them here, so that's going to be -4 equals what? 0, right? Because it's neutral. Actually, I just thought of it. We'll do another one here when we're done. So -4, what must this be? This must be +4. Right? I take that +4 and divide that over all those carbons. There's only one of them. This must be +4. So in carbon dioxide, it's +4, which is perfect. By the way, notice it's -4 here and +4 here. Carbon has the capacity to take on lots of different oxidation states. And that's one of the reasons why it's such a great building block for life processes. Okay. So let's do another one. I'm going to go, oops, I don't want to go white. It'd be hard to see that. Okay. Let's go with one more. Let's take a polyatomic ion. Which one do you want to look at? All right, I'm going to look at table 3.4. I'm going to randomly pull an atom off of the polyatomic ion, or pull an ion off this table, and we'll see. All right, let's go with phosphate. Okay, I'm just kidding about the table. I don't see it here, but suppose phosphate's on there. I think it is. If phosphate is on there, and it would be PO3, that's phosphite actually. Oops, it would be PO4 minus, that's phosphate, sorry. Okay, so let's do this. What's the oxidation state of all the atoms in this compound? So the first one is oxygen, and oxygen's in group 6, so it looks to be -2. -2 times 4 is -8. Okay, and so whatever phosphorus is, it's going to have to add up with the oxygens to give -3, right? Because its charge is -3. Boom, right? So what -8 gives -3? 5. And so the phosphorus atom in phosphate is +5. Okay? So those are the oxidation states of those two atoms in the phosphate polyatomic ion. All right, so let's go look at the rules. I know we've just talked about them. The rules are on page 161. Page 161. And I want to emphasize here that these rules are hierarchical. If any two rules conflict, follow the rule that's highest on the list, okay? So the oxidation state of an atom in a free element is 0, always. It's the highest one, right? This is the most important rule. So copper has an oxidation state of 0. Chlorine has an oxidation state of 0, right? Because it's a free element. Do you see that? Chlorine's by itself. Okay, so the oxidation state of a monatomic ion, this is rule number 2. The oxidation state of a monatomic ion is equal to its charge. So calcium is going to have a +2 oxidation state. And chloride is going to have a -1 oxidation state. Okay? That's rule number 2. Rule 3, the sum of oxidation states of all atoms in a neutral molecular formula unit is 0. So in H2O, I just did this one in a previous slide, it's 0. In an ion, it's equal to the charge of the ion. Okay? So nitrate, just using the notation that I used in the previous slide, nitrate looks like that. Let's come back over here, get a black. Okay? Oxygen's going to be -2 because it's oxygen. It's in group 6. So -2 times 3 is -6. All of these things together are going to equal -1, right? So it looks like this must be +5. Nitrogen's +5. Wow. So nitrogen's +5 and oxygen's -2. All right. Which is, you see what I did here. The oxidation state of nitrogen here is 5, and the oxidation state of oxygen is -2. So 5 times 1 plus 3 times -2 is -1. Okay? All right, that probably is going to take a little bit of practice. Well, it will. Well, it'll take a lot of practice. Okay, now, in their compounds, metals have positive oxidation states. All right? So this is rule number 4. And oxidation states of group 1, always. Always, always. By the way, these first 4 rules are really never broken, okay? So group 1 metals always have an oxidation state of +1. Group 1A metals, I don't know if I said that right. Let me say it again. Group 1A metals always have an oxidation state of +1. Group 2A metals always have an oxidation state of +2. So calcium fluoride, calcium is going to have a +2. In sodium chloride, sodium is going to have a +1 because that's in group 1. Look at the periodic table and prove it to yourself. Here's calcium, which is in group 2. My handwriting is horrible. Okay, so that's rule number 4. And these are just like the charges we were predicting before. So that ought to come relatively easily. Now, number 5 is not so easy. In their compounds, non-metals, okay, this was metals. Non-metals are assigned oxidation states according to the table that lists oxidation states of nonmetals in the margin of the book. And this is on page 161. Page 161, which I'll show you in the next slide. Entries at the top of the table take precedence over entries at the bottom of the table. Okay, what do you mean by that? So let's go over here. Here's some nonmetals. Fluorine's a nonmetal, and it is in group 7. And so it's going to have an oxidation state of -1. Hydrogen is in group 1. So it's likely going to have an oxidation state of +1. Okay? Oxygen is in group 6. Group 7 is -1. Group 6 is -2. Okay? Group 5 is -3. All right? This is, we already saw how nitrogen could have been +5, right? But since it's low on since it's low in this table, it takes low priority, right? It's most likely going to be -3, but if it fights with oxygen or hydrogen, oxygen or hydrogen is going to win because oxygen and hydrogen are higher on this table. All right, I think it's time to do an example. So assign an oxidation state to each atom in each compound. I'm going to try to go quickly here. A, chlorine, we've already seen a couple times. It's a free element, and so it's going to be 0. I'm not going to switch back and forth in colors. All right. B is sodium. It's not a free element. It's an ion, and so it's an ion with only one atom in it, so it's going to take on the charge, right? +1. C, Kf. Okay, so here's a metal from group 1 that's always going to be +1, and here's a nonmetal from group 7, which will usually be -1. But since we knew those were going to equal out to 0, I'm just going fast here, okay? CO2. Okay, I know I did this example in a previous slide, but I'm going to do it again anyway. Oxygen's likely to have -2, -4. Everything equals out to be 0. That's rule number 2, I think, on the table on page 161. So this must be +4. There's only one carbon atom, so that's going to be +4. Can you read my writing? Okay, I think I'm going to change. I'm going to put all of them out here. E, sulfate, -2, and F, oops, how do you spell K? Potassium, this is an ion. Really? That's weird. Potassium oxide. Huh. All right. Well, suppose it's written correctly, and we'll just obey the rules, okay? Weird. So, sulfate. Well, oxygen's group 6, so that's likely to be -2, -8. Sulfur's in group 6 too, but it can't be -2 because we know that whatever it is, it's going to have to satisfy this equation, which is rule 2, right? So what is this? This must be +6. Oh, my handwriting's getting worse. That's a 6. A weird angle, okay? +6 and -2. Can you read that? For sulfate, +6 and -2. All right, so this is really weird. I've never seen this before, but let's do it anyway. Peroxide, I guess. Let's say it. All right, so this has a tendency to be -2. Okay? And this had a tendency to be +1. But I said tendency, wait a second. Rule number 4 on page 161 says this is always going to be +1. And rule number 5 says this is likely to be -2, right? And it refers you to the table in the margins. But remember, this is the top rule that wins. So it must be this guy wins. So this not necessarily wins. Let's go here. +1. That gives us +2. And rule number 2 on that table on page 161 says that these have to equal, for neutral compounds, has to equal 0. So what must this be? This must be -2, right? And there's 2 of them. So we've got to divide that -2 out over both of them. Looks like the oxidation state for oxygen here is -1. Wow. Ooh. UgLy. So here's one where rule priority matters. All right, that's example 4.16. I think we've got another example here. Actually, yeah. Okay, so now we need to talk about oxidation reactions, oxidation reduction reactions. So oxidation reduction reactions, here's an example of one where hydrogen is combining with oxygen to produce water. Okay, let me just quickly go through here. I'm going to put this back in red. This is all blue, red, boom. Okay, so what's the oxidation state of hydrogen here? It's a free element, right? So it's going to be 0. And what's the oxidation state of oxygen here? It's a free element, so it's going to be 0. Okay, but these are not free elements. These are compounds. This is likely to be -2. This is likely to be +1. And so -2 times 1 is -2 equals 0. This must be +2. Too small. Sorry, my pen's not liking that. And there's 2 hydrogen atoms here. So 2 divided by 2 gives me +1. Can you read that? Oh, I hope you can. All right, +2 and -2. We've done that one before. So, hydrogen goes from a 0 to +1. And oxygen goes from a 0 to -1. Well, one of these guys is gaining electrons. Who's gaining the electrons? Oxygen's gaining the electrons. You see that? It's getting a negative charge. And remember, reduction is gain of electrons. So this is a reduction. Okay? And the other thing is the oxidation Okay? Man, sorry about my handwriting. All right. So this is an oxidation reduction reaction where hydrogen is being oxidized and oxygen is being reduced. By the way, it's no coincidence that oxygen is not being oxidized. Right? Can you hear those words? Oxygen would be oxidizing other people, right? Hey, I'm oxygen. I'm gonna oxidize you, right? It's not really a great word picture, but perhaps that can help you appreciate that. Oxidation is not going to be oxidized. Oxygen is going to be reduced. All right, let's consider another one. What about oxidation reduction reactions where we don't have oxygen? So let's go here again and say, what is sodium? I really should write bigger. I'm gonna write bigger here. Hopefully it's not too big. So what is the oxidation state of sodium here? What is it? Hopefully you said it's 0 because it's a free element, right? What's the oxidation state of chlorine here? Well, hopefully you said 0 because it's a free element, right? What's the oxidation state of sodium here? Well, this is an ionic compound. We've seen this several times. This is +1 and this is -1. And remember that in an ion, the oxidation state of the ion is the same as its charge, right? So this is going to be an oxidation state of +1, and this is going to be an oxidation state of -1. Chloride is, okay? So sodium chloride, and Tro says here, electrons are transferred from sodium to chloride, right? And can you see chloride's got an extra electron here? Forming sodium chloride. Sodium is oxidized because it goes from 0 to +1. We lost electrons. Lost electrons. Oxidation is loss of electrons. And chlorine gained electrons to become chloride. And reduction is gain of electrons. So chlorine is reduced, sodium is oxidized. All right, think we just have a couple examples now, right? So use oxidation states to identify the element that is being oxidized. Example 4.17. This is on page, I guess, 163. So we come here. I'm just going to go through and make some notes to myself. I'm going to say the oxidation states of these things. I'm going to do them all real quickly, okay? So for magnesium, I can see it's a free element, so it's 0. Hydrogen is a free element, so it's 0. Water, I've done a couple times. Do you mind if I do this a little bit more quickly now? It's oxygen is -2. Hydrogen is +1. Okay. Magnesium, okay. This is a little bit, I'm going to put a big box on it so you know it's a 0. It's not a circle, it's a 0. Okay. Well, magnesium hydroxide. Well, magnesium hydroxide is really magnesium 2 plus and 2 hydroxides, right? We've seen that before. So I can see that magnesium is going to be +2. And hydroxide, I don't know, we haven't done this one yet, so let's do it now. Hydrogen has a tendency to be +1. Oxygen has a tendency to be -2, right? So +1 times 1 gives you +1. The charge is -1 in this, right? And so this must be -2. -2, and you've only got one oxygen here per particle, per hydroxide. And so that -2 is going to have to go all the way on that. So that's exactly what we thought, right? We predicted -2 and +1, and that's what we got. So this is -2, running out of space here, and +1, okay? So what changed? All right, so magnesium changed, and it went to +2. And some of these hydrogens went from +1 to +1, but others went from +1 to 0. Okay? So this goes from +1 to 0. Can you see how the oxidation state is going down? This is gaining electrons. And this is losing electrons, right? From 0 to +2. So this is loss of electrons. Oxidation is loss of electrons. Reduction is gain. So now I'm ready to read this question again. Use oxidation states to identify the element that's being oxidized. Okay. Magnesium is being oxidized because it's losing electrons, right? And the element that's being reduced, okay? And it looks like hydrogen, some of it's not doing anything, but some of it's being reduced. So hydrogen is being reduced. Okay? All right, one more example, I think, and then we'll be done. And that is, no, 2 more examples. Okay. So first of all, this one, I'm going to go magnesium. I'm going to leave the states out because they don't matter here. I hope that doesn't bother you. Magnesium oxide. Actually, don't even need to balance it. Plus calcium hydroxide. Gives 2 waters. I'm going to write everything out, and then I'll use different color calcium bromide. Okay, and then the third one is zinc plus iron, 2 plus, produces zinc, 2 plus iron. Okay, now I'm going to get a black marker here, and I'm going to go through and do all the ones that are easy first, okay? So magnesium is going to be 0, and oxygen is going to be 0, right? Zinc is going to be 0, right? This is going to be +2 because it's by itself. You see that? This is going to be +2, and this is going to be 0, okay? Now, there's some other ones that you might think are easy, and I'm going to agree with you. Magnesium is in group 2, so it says it's always going to be +2. Oxygen's in group 6. So you're expecting that to be -2, and sure enough, look, it's 1 to 1, no charge. That's easy, okay? HBr. Bromide is in group 7. It wants to be -1. Hydrogen is in group 1. It's a nonmetal in group 1. It wants to be +1, so that's legit. Calcium's in group 2. It wants to be +2. It will be +2, always. +2. That's rule number 4 in that table. Bromide here, -1, right? Can you see there's 2 of them? So 2 -1s is going to balance out 1 + 2. Okay. And then oxygen we've done a couple times, so if you don't mind, I'm going to go right through it. +1. Okay? And these are hydroxides. We did hydroxide in a previous slide, and we saw that hydrogen was +1, like we're expecting, and -2. It'll be rare exceptions when oxygen and hydrogen are not +1 and -2. Okay, I think we've done all of them. Oh, wow. Okay, so determine whether each reaction is an oxidation-reduction reaction. Yes or no. If the reaction is oxidation-reduction, identify the oxidizing agent. Ooh, okay. So if magnesium is going from there to 2+, it looks like it's being oxidized. So this must be the oxidizing agent, right? Okay, if hydrogen, what's changing here? Oh, nothing's changing here. Hydrogen is +1, +1, +1, and that's it, +1. Bromide's -1 and -1. Calcium's +2. Okay, this is not an oxidation reduction reaction. How do you spell redox? Redox, okay? And zinc is going from zinc 0 to +2. It's being oxidized, right? So this must be the oxidizing agent. Okay? Well, if this is the oxidizing agent, this is the reducing agent. And if this is the oxidizing agent, this is the reducing agent. Okay? And that's it. All right, so this last example is writing the equation for combustion reactions. We've seen this a few times. I'm going to do it quickly. Methyl alcohol. We remember that combustion is combination with oxygen. In the case of hydrocarbons and carbohydrates, it is to produce carbon dioxide and water. So we have CH3COH, which is liquid methyl alcohol, plus O2 gas, produces carbon dioxide gas plus water, and it's probably going to be a gas also, okay? Because it's hot, right? It's coming out of a flame. So let's balance this out. Carbon to carbon is 1 and 1. So far so good. I'm not going to make any notes here. Let's go with a different color. Okay, hydrogen is 1, 2, 3, 4. So if I change that to 2, that'll make that 4. All right. And how many oxygens are here? 1, 2, 3. 1, 2, 3, 4. So if I take this, let's see, what do I do here? If I've got 3 over here and 4 over here, I need 1 more over here. So I think if I change that to 3 halves, right, that'll give me 1. Yep, that'll give me 4, okay? You see 3 halves times 2 is 3. That's 4. 1, 2, 3, right? 3, 4. Okay. So the last thing I do now is I multiply everything by the denominator of any fractions. So if that's the case, this goes to 2. This goes to 3. This goes to 2. And this goes to 4. So the answer, the answer, 2 moles of methanol, liquid, because it says liquid, plus 3 moles of oxygen gas, because it says combustion, right, produces 2 moles of carbon dioxide gas plus 4 moles of gaseous water, steam. All right. Okay. Send me your questions. Hope that's helpful.